Hi, during this session I'm going to be talking about electric potential energy, and I'm using the diagram on the left here just to kind of highlight the similarities between electric potential energy and gravitational potential energy. So gravitational potential energy, if we have a particle in a certain location, in a higher location, then what happens is gravitational potential energy increases. Now, with electric potential energy, the location within an electric field allows us to work out the electric potential energy of this charge, and it can be calculated as it moves from one location to another, and that's the potential difference, which is the voltage multiplied by the charge of the particle which we're thinking about. So please try and keep that in mind, as there's a constant similarity throughout the fields and forces units. So let's go through some meanings now. What is electric potential energy and how can it be calculated? Well, an electric charge produces an electric field around it. We accept that. And if we want to move a charge closer to a similarly charged sphere, so if I have a positive charge, then what I'm going to do is I'm going to have to push against that repulsive force. So I'm imagining a positive point charge which I've placed into this field, moving it from B to A. That's obviously going to take some effort. So what I'm doing here is I'm increasing the electric potential energy. So the work that I have to put in pushing this is going to be equal to the gain in electric potential energy of this particle. So if I let go of this imaginary particle, what will happen is it will immediately move away because of the forces of repulsion, so it will be losing its electric potential energy but gaining kinetic energy, so energy is still conserved. So that's the idea of electric potential energy. Notice there's no numbers here just yet. So electric charge also created the related quantity of electric potential, which is the voltage. Now, this is a measure of work required per unit charge to move to that point. It's probably the more useful gateway to numbers. So with that stated, the work done on a charge is going to be can be calculated from the equation that voltage is equal to the work done divided by the charge of the unit. And the unit for electric potential is joules per coulomb, which is obviously the volt, which is something which we've mentioned before in previous videos when talking about electric potential difference in topic 5, as it turns out. So there's some repetition here which is kind of useful. So work is done in moving a 2 microcoulomb charged object from very far away to point A. And that is 1.5 times 10 to the minus 6 joules. So that's the amount of work done. What is the electric potential at A? So we've got all the information we need. You should be able to calculate that using the formula above. So we recognise that the voltage is going to be equal to 1.5 times 10 to the minus 6 divided by 2.0 microcoulombs, which comes out as 75 volts. So that's the electric potential at A for this point charge. Now, no work is done to move a point is the electric potential energy. Okay, so the reason I didn't mention that earlier on is because we're thinking about, in this case, the amount of energy it takes to move the point charge from infinity up to this point. So it needs to be a number that you know, and obviously this is in a perfect physics world, because no object can travel from infinity and not have to interact with other objects which are out there. So electric potential, we've got a further formula here to make you aware of. Electric potential can also be derived through integration of Coulomb's law. Now, in IB physics, for the diploma, you don't need to worry about your ability to integrate. However, if you can, or if you want to do that, then you should recognise through the integration of Coulomb's law, we can work out that the voltage is going to be equal to Coulomb's constant times Q divided by R, and this is also equal to, as we know, Coulomb's constant is equal to 1 over 4 pi epsilon 0 multiplied by R. So they've got two ways to calculate voltage. So putting a question here, find the electric potential a distance of 0.5 times 10 to the minus 10 meters from the proton of a hydrogen atom. Okay, so that's what we've got to do, find the electric potential here of a proton. So we know all the information here. We know the charge of a proton, and we know the distance away from it, so therefore we should be able to plug in the numbers, and it comes out as 29 volts. Okay, so another formula which allows you to work out values if they're unknown. Now, equipotential field lines. If we think about the last problem, there was no definitive location of where the particle was. It was said to be 0.5, let's just click back, 0.5 times 10 to the minus 10 meters away from the proton. It wasn't north, south, east or west. The reason for that is everything at that distance is going to have exactly the same electric potential, and this allows us to have what's known as equipotential field lines. So we can see the field lines in dark blue here, and the spotted lines, these are lines of equipotential, so where there's a similar potential. Around a point charge we have concentric circles moving out, and between two parallel plates all the lines will be running parallel. So our rules are equipotential field lines display points in space that have the same potential. They are always normal to the field lines. Okay, so they'll always cross over the field lines at 90 degrees, and will follow similar field line density. Now, that's probably shown best if we think about the field lines in this situation, and what we can see here is that where there's likely to be more field lines, then we can see that there's likely to be often be able to show that the equipotential field lines are often grouped closer together. Equipotential due to more than one point charge. Okay, so this is something to think about, but actually it becomes quite simple. Electric potential is a scalar property, so that means all you're going to do is add up the voltages caused by each of the surrounding point charges, and that total value should give you the electric potential at that point. So therefore it's just going to be the sum of all the potentials, which we know can calculate by K times Q1 divided by R1 for the first charged object in this universe, Q2 and R2 for the next object, Q3 and R3 for the next object, and so on and so forth. So that's how we can work out the electric potential. I should also mention the electric potential gradient. Now, the change in electric potential per distance is also equal to the electric field strength. So what we have here is, if I change the voltage from one place to another, the change in voltage, let's say from V1 to V2, divided by the distance in space between from V1 to V2, would give me a number for the electric field strength. So it's another way to be able to approach questions like that. Final recap, electric potential difference. Now I've mentioned this before, and we're just going to recap again. So remember, electric potential difference is the work done to move a charge from one point to another in an electric field divided by the charge. So it's work done per unit charge. And we've got to remember that this change in voltage, this electric potential difference, is work done to move the divided by charge. So the change in field strength divided by charge, and that can give us from our earlier calculations. So therefore the change in field strength divided by the charge involved gives us the electric potential difference. This is another way to think about the electric potential difference, another way to work it out when it's changing from one point to another, using that idea earlier on from gradient. And with that, that gives you everything you need to know about electric potential energies and differences